I want to acknowledge the work of my co-authors. This is Jita Hosch from my working group and Professor Frede from the university in Rio de Janeiro. So actually these two persons did all the work. And my contribution is simply to give that presentation and to enjoy my life here. So this work is on fatigue crack propagation under non-proportional loading. And there are a lot of influence factors which I'm not going to discuss in detail due to time limitations, but there are quite a lot of them, and they are not fully understood, and at least we don't understand them, and therefore we started a new experimental campaign on loading thin-walled tubes under axial load and under torsional load, and combine these two loading cases, axial and torsion, in proportional and non-proportional way. Certainly we did some basic experiments on the tension compression alone with some maximum force on these tubes. The tubes had an initial starter notch, which you can see here, and well, under pure tension there is nothing astonishing what happens. The cracks start at the notch root and grow straight through the tube, and under torsion, well, we learned from this experiment that we have to paint the surface in white color in order to get nicer pictures. And what you see here as pixel is a laser dot pattern in exactly 1 millimeter distance of each dot, which eases us to measure the crack length from optical inspection. And under pure torsion, you see that 4 cracks initiate and grow with the specimen in a curved way. And I should mention that the R ratio in all our experiments is -1 for tension and for torsion. So these are some figures on results of crack growth under proportional loading, under 45 and 90 degrees out of phase loading. And you can see what happens to the crack path. And what we did is, in trying to understand what's going on, what we did is looking onto the environment of the cracks and the crack tips and get the deformation field by digital image correlation. In the easy case of a uniaxially loaded specimen, you can identify displacements upward and displacement downward, of course, and you see how the crack opens and closes. And in the lower part of these figures, you see strains, calculated strains from the deformation field. However, you see here that we have calculated strains across the crack surfaces, and therefore you can say that these are not real strains, pseudo-strains, you can say. However, these pseudo-strains give an indication on what is the crack opening profile at a certain load combination. Well, however, the crack opening profile can also be identified more or less exactly looking closer to the crack surfaces. And for example, you can see that at minimum loads the crack is closed, and if you increase your load from minus 43 kilonewtons to 18, minus 18 kilonewtons, there is hardly any displacement. And if you increase your load to plus 43 kilonewtons, you see here the crack opening profile. The crack tip itself is located at the coordinate 0 here, and what is given here is a distance from the crack tip. Ahead of the crack tip, where the material is, then these are real ligament strands, and behind the crack tips, these are crack openings. Well, if you investigate such deformation fields, you can find such curves force over crack opening displacements. These are the digital measurement results here, and we have seen such type of curves in this model by the first one by your presentation. So this is what comes out, and the blue lines is what we calculated in the first attempt using Chabosh model for our, I should have mentioned that it is mild construction in steel, and we try to get that by a node release scheme. And what you can measure as a crack closure load and what you can calculate as a crack closure load considerably deviates, but this is not the real point of my presentation today. We inserted measured crack closure points in calculating cyclic J integrals and correlate that with measured crack growth rates, and we're quite confident result which came out of this calculation. However, it's not possible to do that. This is a release scheme, for us at least at the moment. So, this is a short glance on measurements for the pure torsion loading, where we get 4 cracks. And again, the displacement is plotted here between these 2 points across the crack surface. For the one, for the first and the second crack here. And what you can see is the crack opening displacement over the torsion. And for the slightly longer crack, the blue line came out, and we see at negative torsion moments, the crack is closed and it opens when the torsion is positive, and the crack number 2 does just the opposite. So while the first one is closed, the second one is opened, and vice versa. And in the middle here, in between, there is a state of torsion where both cracks are open. Now there is a slide where I don't get the movies running individually. I brought with me some movies, which I was not able to get them running within PowerPoint because of limitations in space or so. This is one of these movies. On the left-hand side, you see the force, the applied force, and the applied torsion moment, and this goes round in this ellipse here, indicating a 90 degrees out of phase tension torsion loading. And what is plotted on the right-hand side are the strains in Y direction. The one that we inserted at the crack tip, as close as we could identify the location of the crack tip, is that point here. We inserted a tangent line to the crack, and this is our X direction, and perpendicular to that is our Y direction. So Y, epsilon YY indicates some mode 1 crack opening. And then, hopefully it runs. No, it does not. Okay, this starts from the closed position. Now the crack opens. There is a point running around there. I don't know whether you can see it here running in the back seats. So here it's closed again, and then if you turn around one more, it opens here and closes here. And then you can repeat that for a couple of cycles, and each movie takes me a minute, and I do not have too much time for that purpose. And you see here approximately, movie is over. I have put here in the PowerPoint a situation of where moments and the force at the moments are at that point here. Here's my coordinate system, and this is the profile which we can measure at that point. And it is close to mode 1, and when the crack is smaller than that, the figures are all very, very similar. And please note that when the crack initiates here in the notch loop, it is under locally, it is uniaxially stressed and nothing else, because at the notch loop there cannot only exist uniaxial stresses. So there is no non-proportionality at the initial stage, and the crack grows under mode 1. However, as it becomes longer and grows out of the notch field, this non-proportional interaction of the 2 loading cases inserts gradually. And what you can see here at that point is some disorientation. It's not very symmetric across the x-axis, no longer what you see, and there is some higher stresses ahead of the crack tip pointing here in this direction. And well, I don't know whether the chairman will allow me to show the next movie. On the right hand side now, I have plotted the XY stresses. So this is now mode 2, what we can observe at the surface. And on the left hand side, no longer forces are and moments are plotted, but the strains in YY over the strains epsilon XY. And you see what happened to this original ellipse if you apply simply these loads. So here this is the point where it's closed, and the point is running here. It approaches the point where it's wide open, and then it closes again. And now we have to interpret what's going on here. For example, I pulled out this point here, where the maximum local strain in mode 1 is situated at that point, and this is the associated mode 2 strain, epsilon xy. And my point is now, you see what happens here during such a cycle, while the crack is closed, and the crack is closed, while the epsilon yy strains are negative, close to that value. So here this is a closed crack. And during that closed crack, you can see that the strains in xy direction are changing. So this simply means that the crack surfaces are moving against each other, although you have a compression on the mode 1 on the crack. And while the crack is open, by the way, right-hand side of this figure, you see that the shear strains are a bit larger than under compression. However, this crack closure under mode 1 does not really influence the mode 2 contribution. And okay, I should have put on my glasses. So the point I have just shown you in the previous two figures and in the two movies, the crack tip was located here at that point, and I showed you that point because at that instant the crack became a kink. Maybe in the rear scenes you don't see that, but the crack now grew in that direction, and now we readjusted x and y coordinate systems and again plotted strains epsilon yy. These are now strains in this direction, and again here moment over force, and I have the associated movie with me. If we can show it, then I do that. Otherwise, we can watch that in the break. No. What's the next one? Okay, epsilon y, it opens here, then it closes, and you now see how closure occurs. So closure occurs starting from the notch point. So here it opens from here, then the opening goes to that point here, and then it starts closing from that while it is open at that position, and finally it's closed here, and so on, and so on. But to our opinion, it's terribly complicated. Well, you saw this situation, and this is what happens when we plot epsilon xy over epsilon yy for the point where maximum opening occurred. It looks like that, and you see again, here is a red point and so on, and now curvature occurs, and to destroy everything, let us watch some final movie, perhaps. So the crack tip is now here. So there is some curvature occurring, crack tip is here, and now you see again these epsilon yy strains. It's closed now, the crack opens from here, goes to that. You have a red point here, a red there, it shifts here. And this is an indication that now the crack tip is allowed to bifurcate. We have observed such occasions that at this position we have a bifurcation of the crack tip. Well, let me summarize that. These are just figures from the movie I have just shown you. Accompanied by what is the shear strain for these positions, and coming to my summary. So this digital image correlation allows measuring crack closure and crack tip strain fields, the simulation of crack closure. Numerical one may provide erroneous results due to the node release scheme and the plasticity model. This is a different story. For the for the uniaxial case, the cyclic effective delta J integral is able to correlate background rates, more or less. Well, one finding is what others, or we have also found in previous investigations, that the surface mode 2 related displacements are observed while the crack is closed under mode 1, and unexpected crack tip strain fields are observed due to non-proportional mixed mode loading. And I do not present a new hypothesis, we haven't understood everything in detail yet.
Thank you very much. Thank you.